Hello and welcome back. In this episode, we shall introduce ourselves to the mathematical and statistical concepts that you need to know as a data scientist. But first, I'll introduce myself. My name is Juma Shafara, and I'm a data scientist at Raising the Village and instructor at Data Idea. And this year, I set out to help people become data scientists by covering data science concepts in a simple and intuitive way. So far, we've looked at Python and Python libraries like Matplotlib for data visualization, Pandas for data manipulation. We've introduced ourselves to SQL and version control with Git and GitHub. And as we continue in our roadmap, which I'll link in the description, we'll be looking at mathematics and statistical concepts for data science. So this video will be for total beginners, but also it will be a way to confirm to already practicing people that the concepts that they have learned or that they're applying are the right ones, okay, for a data scientist. So when you finish this video, it doesn't mean that you've learned all the mathematics and statistics. It just you will be having the right picture as you progress in this journey. So the first item I would like us to look at is vectors. Okay, and vectors will fall under linear algebra and the mathematics part of data science. But you don't have to learn all the mathematics. What you should just know about vectors is that a vector is just an ordered list of numbers, and we use this as a structure for storing data. Okay, so if we have like edges we want to manage, or measurements of an object, okay, like lengths, we can use vectors to store that data. Okay, and here I have an example where I'm creating a vector using NumPy. NumPy is a Python library for for dealing with mathematical stuff in data science. So here I create a vector with only two numbers. I can add a third number, and you can assume maybe this is some measurements of an object, and we have maybe 3 centimeters, 4 centimeters, and 5 centimeters. This is how data scientists will be managing measurements, okay, but numbers of any kind, even names, okay. So we create one vector like this. As you can see, it's just a list of items. Now the other item we want to look at is a matrix. A matrix is a two-dimensional array of numbers. So for vector, we have only a row, maybe we have a list of items, okay? But sometimes when we are managing data as data scientists, we have items that we want to manage maybe together. So we have maybe measurements of length, we have measurements of height, we have measurements of width, and we want to manage these items together. Okay, so we can use a matrix. So it will help us by giving us a structure similar to a row and column structure. Okay, like this example of a matrix that I have created, and as you can see, we have this can be like one column where we have 1 and 3. Okay, this can be measurements or in maybe lengths. Okay, and then we have another column where we have like 2 and 4, and this can be maybe a measurement, maybe like of width or edges in our data set. So matrices are really, really important, and we use them to, as I've said, to store quantities or to organize our data sets for just analysis and maybe modeling. Okay. Now that I've mentioned vectors and matrices, there are just some basic matrix operations that you may just want to know as a data scientist. Okay, so you may want to know how to add and subtract matrices. Here I have some example, and again I'm using NumPy. NumPy is a library for mathematical stuff for data scientists. And here I am creating two matrices, matrix A and matrix B. And to add any two matrices, by the way, here I have printed them. This is how they look like. Okay, we can add any two matrices by using a plus sign. Okay, if we created them with numpy, okay, and this will just add the matrices element wise. As you can see, 1 and 5 will be added to make 6, then 2 and 6 will be added to make up 8, and then 3 and 7 make up 10, 4 and 8 make up 12. And if we had more items, okay, this is how they would be ordered. Again, element-wise subtraction will also do the same thing. As you can see, we get 1 minus 5, which gives us like minus 4. And the way we subtract is we just use this minus sign. We may also want to multiply matrices. Okay, this is how we do it. We just use this little asterisk. And this is element-wise multiplication, where each element is being multiplied with a corresponding element in the other matrix. So we can see that element 1 here in matrix A is being multiplied with element 1 in matrix B. Okay, and then we have this result, and it goes on until the other elements. Okay, it's really simple. And then there is this dot product. So our dot product here is your usual matrix multiplication, okay, where you get the product of the sum of the product of the row and column values. Okay, so if I just print this, and maybe we can have a look, we'll see that if I say printed A and B, um, let me just print them on separate lines. So in this case, we would be having 1 times 5, okay, plus 2 times 7, okay, row by column multiplication, usual matrix multiplication. You may also want to know the transpose of a matrix, and when we transpose a matrix or a table, basically in this context we are just converting the rows to become the columns and the columns to become rows. Okay, and we have an example of this matrix that I just am using here. We can see that in the first part here we have 1, 3, 2, 4 as our columns, and after transposing we have 1 and 3 as row 1, and then we have 2, 4 as row 2. Now they are swapped. Again, I can't cover everything in this particular part, but you can go search about say the inverse of a matrix, the determinant of a matrix, and then you can search about eigenvalues and eigenvectors. All right, let's talk about derivatives and gradients, and this comes from calculus. Also the mathematics bit of data science that you may be requiring to know. Yes, you really thought that calculus was useless. No, it isn't. So I just want to talk about two concepts. One is derivatives, and then the other is gradients. And a derivative basically represents how a function changes as its input changes. And to illustrate this, I have this function that I am setting. Okay, I have x squared here plus 3x plus 2, and to get the derivative I'm using this simple, it's called SymPy. I don't know how you read it. It's called SymPy. It's a library that just has some stuff to do with calculus, and to get the derivative I just use a method from that called diff. Okay, to get the derivative of a function x f with respect to x. Let me first run and then I talk about what this derivative again means further. Okay, so let's first import our diff and symbols. All right, so we have here a derivative of x squared plus 3x plus 2, okay, as 2x plus 3. And what just happened here is basically we got for this particular number here, we got this power 2 and we multiplied it by our x here, and then we reduced the power of x by 1. Okay, it's the same thing that happened here. We reduce the power of x by 1. Now for this other number here, the power of x is actually 1, so when we reduce it by 1, it becomes 0, and any number to power 0 becomes 1. Okay, so that's why we end up with just like plus 3. Now about 2, what happened to 2 here is that 2 is like 2 times x to power 0, 2 times x to power 0. Okay, and when we reduce that and we multiplied this figure by 0, okay, it just disappeared. When you multiply anything by 0, it is 0. Okay, so yeah, we end up with a result like this. And what this actually means is, as I said, it just represents how a function changes with its input. For an example, a derivative can tell us how fast you are moving. Okay, say if you are in a vehicle, how fast you are moving. That's the derivative. The speedometer will illustrate this. Okay, that's like the derivative. Now the gradient in this context, it will just tell us the direction and the steepness of our function. And same case for if you are like moving, maybe you are climbing somewhere, the gradient will just show us the direction that you are moving and how steep this hill you are climbing is. And in this context, the derivative is the same as, rather the gradient is the same as the derivative, but in another context, okay, the gradient can represent something a bit bigger, which is out of the scope for this video. So I'm gonna put a link in the description so that you can search more about this derivative and gradient thing. We use this so much when we are optimizing algorithms, especially in machine learning. We basically try to find the quickest way to train an algorithm to understand the data. All right, let's talk about probability distributions. Probability distributions basically describe how the values that we have gathered through any data collection process are distributed. And I'll be talking about only the uniform, the normal, and the binomial distribution. And there is so much more. I will put a link in the description also, so you can research on those, more on this, and also any other distributions that are existing. The first distribution will be the uniform distribution. And in a uniform distribution, all values within a range, okay, are equally likely to occur. I have this little graph to demonstrate this, and here I am visualizing how likely the heads and tails of a fair coin are likely to occur. If we've tossed any number of times, okay, we can see here that the heads and tails of a coin all have a probability of 0.5. Well, they all have a chance of 0.5, have a chance of occurring of 0.5. Okay, so yeah, this kind of visual will illustrate what a uniform distribution sort of looks like. Another example of uniform distribution, or another example where uniform distribution will occur, is when we collect data of rolling a fair coin, a fair die, and then drawing a card from a well shuffled deck. Each card has an equal chance of turning up. Okay, so that's uniform distribution. The second distribution I want to talk about, which turns out to be one of the most important distributions in data science, is the normal distribution. So the normal distribution is symmetric and centered around the mean, and I'm going to talk about the mean later, just at the bottom. Right, the mean is basically the average of the observations. Here I have an illustration that is describing the distribution of the ages of the Nobel Prize winners, and what we can take out from here is that it looks like the majority of the Nobel Prize winners are around 60 years. This is not a perfect data set. I generated this one, and also what we can take out from distribution is that the chances of getting a Nobel Prize are lower with younger people and also lower with much older people. This is what this distribution shows us. The normal distribution, as you can see, it's symmetric around the mean. The mean is around 60. Okay, so the other side is sort of like equal to also the other side. It describes here the chances of people of these ages winning a Nobel Prize award. Other applications or other places where normal distributions occur are measurement errors, stock price fluctuations, IQ scores, heights of people anywhere. Basically, a lot of natural things in this world follow or occur in a normal distribution. The other distribution, which will be the last one that I will talk about here, is the binomial distribution. The binomial distribution models the number of successes in a given number of trials. To illustrate, I have this simple graph. By the way, all these graphs, I have generated them using matplotlib. I have a video that introduces people to data visualization with matplotlib. I'm going to link it so that you can check out how to come up with graphs like this. Okay, but here the binomial distribution that I am illustrating is of tossing a coin. Okay, here we can see that if our success is the head of a coin, if our success rather is the head of a coin, okay, and we toss a coin 10 times, we can see that the most likely number of times a head will occur is about 5. Okay, and it takes on half of the chances. So it means that also if our success was a tail, the tail was also gonna have equally the same number of times of occurrence, about 5. So this is a binomial distribution. Now, when you look at this binomial distribution, it may be looking similar to this normal distribution, but this is only because the coin in this context is fair in such a way that the chances of a tail and a head occurring are equal, and that's why the shape turns out to be like this. But if we got our coin to be biased in a way, we may see that this distribution, we are having taller bars on either side and maybe very shorter bars on one side. That idea is by the way called skewness. And also I have links to the learning materials to discuss more of that. Again, in this video I just want to talk about the key concepts at the top layer. Other situations where binomial distributions occur is the number of defective items in a batch of any production, the number of customers who click a given ad on YouTube, okay, this number follows a normal distribution, rather a binomial distribution. The number of students that pass an exam also follows a binomial distribution. Okay, and uh, last but not least, let's talk about expectation and variance. So expectation and variance is a very common thing in data science, and it's a thing that you'll be glad to just familiarize yourself with. And what expectation does is that it tells us where the center of a given data or distribution is. Okay, if we've collected any data, where does the center of the data lie? And understanding the center of the data is very, very important, um, as a lot of things usually are lying around the center of the data. More about the center of the data is gonna be linked in the description so that you can just jump to that and find out why understanding the center of data is so important. Here I have some illustration of how we can calculate the expected value of the expectation rather of a given data. Okay, and this video isn't to show you how to calculate this. I'm just covering the concept so that you know it is there and you can do more about it. The other one is, the other part you're looking at is variance. Okay, and variance just tells us how spread out our values are around the mean. Okay, so now that we know the center of the data, how spread out are the values, okay, about this center that we have observed. The applications of expectation and variance are in portfolio management, insurance risk management, machine learning, hypothesis testing, and so much more. And these are things that are occurring and being and data science is being applied to, okay, every other day. All right, so let's look at descriptive statistics. Descriptive statistics just some items that we find about the data to help us understand or give us a picture of what this data actually represents and means. Here we look at especially measures of central tendency, as hinted on a bit earlier on. And then we focus also on the variation from that center, and there are a few statistics, yep, that we want to look at. We want to look at mean, we want to look at median, we want to look at mode. First, mean. The mean is usually describing, the mean is the average of all the data that we have collected, okay. Then the median is if we arrange the data that we have collected in some ascending or descending order, the middle value, okay, in this data is actually what we call the median. And then the mode refers to the number or the value in our data that is appearing most times, okay. And then the standard deviation also, which is a measure of variation, just basically tells us how spread on average the data points in our data are from the mean. And the difference between standard deviation and variance itself is that standard deviation gives us the differences in the actual units of the data, whereas variance is having that difference squared. So you can infer that to get the standard deviation, you can just get the square root of variance. Here I have some code using NumPy to obtain these values, and for this sample data that I have, the mean is 15, which is the average of all these values, and then the median, which is the middle point when they are arranged in ascending order, it's 15. Then the mode, which is the number that is appearing most number of times here is 10, which is appearing, I think, like 2 times. And then the standard deviation is 4, which shows how these values are deviating from 15 on average. The average is about 4.12. So finally, we shall talk about regression analysis. And regression analysis just helps us understand relationships between variables, and also understanding the relationship between variables, usually numeric, can help us predict outcomes, predict any outcomes for an sort of an extrapolation, extending the understanding. So here is the thing. Regression assumes a few things, and I'm not going to talk about everything that regression assumes, but one thing which is very crucial is that it assumes that a straight line can describe this relationship between any two variables. If we have like maybe age and then we have income, regression analysis will assume that a straight line can be able to tell the relationship between somebody's age and the amount of money they are that they are earning. Here I have some code, okay, to do some regression, and I'm not gonna go deep into this code. What I just want to show you is is this illustration that comes from that code, where we have some data points about some actual values, y and x, and then this simple red line here is what we call a regression line, and basically it is showing that for this particular context, that as x increases, okay, y increases. And even though it's not general over time, I mean, even though in some cases it's not necessarily true, we can observe that it's fair to generalize that as this value x, okay, increases, maybe income also y increases, whether x age also y increases, y as our income. So this sort of line, okay, explains that. More on regression analysis is available in the description. Also, I have these materials on the Data Idea website. Okay, so just make sure to check out. So regression analysis is applicable in very many cases uh, when we are doing predictive modeling, okay, when we are doing time series forecasting. You want to find out if the previous years we've been getting this amount of income, what happens in the next year, or if we've been getting this amount of rainfall, what will happen in the next period, okay. And then causal inference, when we want to find what causes which, okay, we can use regression analysis to find out if it is indeed true that a given thing x can influence another thing y, okay. And then feature engineering. And feature engineering is a thing that is slightly advanced out of the scope of this context. So again, there are learning materials on the Data Idea website for you to understand what feature engineering means in detail. Okay, if you've reached at this point, it means that you are really, really motivated. And here's the thing, learning is not a really simple thing, and it is very, very continuous. So you shouldn't expect to get everything there is, but it's important to get a good amount also for you to begin applying concepts and get started. And this video, I have highlighted some of the concepts that you should know, okay, and so take this as a stepping stone onto the next level. Also, stay hooked for the next upcoming video, where I'll be again covering another really, really important concept that you need to know as a data scientist. And until then, see you, thanks, and bye bye.